Well, thank you very much. Let me say that I'm really glad to have a chance to give a talk here at the SETI Institute, where there are many scientists and people working in the SETI business that they really admire for what they do. They have the vision of the future. They do work that, in the quotes, established scientific community sometimes is not yet fully understood, but in my opinion, is a profound research and a step forward. So let me come straight to the point. I am not a member of the SETI Institute, but I have to say that I've been working in SETI for many years, and I am a member of the SETI Permanent Study Group of the International Academy of Astronautics. Now, in this regard, we came to consider many possibilities, that is, doing SETI not just in the ordinary ways, that is, using radio telescopes, but possibly use spacecraft in order to do SETI from different new point of views. So what I'm going to tell you about today is an idea that was actually put forward by Professor Frank Drake, as far as I can remember, back in 1987, in a conference that was held in Hungary, that was called the second Bioastronomy Conference. And Frank Drake came along and he gave a wonderful talk about the possibilities of using the sun. Let me go back. This is the title slide. Using the sun as a gravitational lens. Now, of course, he was thinking about doing so for SETI. That is, the gravitational lens of the sun, as I will explain more in detail. So this is just a very preliminary, intuitive idea of the story. The sun has the largest possible mass in the solar system. We all know about that. Now, since according to the general theory of relativity of Einstein, space-time around any mass is bent, so it becomes curved, the bottom line is that radio waves reaching the sun from wherever in the universe, more specifically in the galaxy, are made to focus by the sun mass. And so the key point in the story that I'm going to present is to build a spacecraft and send a space mission out to the minimal focal distance where we can pick up these signals highly intensified by the gravitational lens of the sun. So this is what Frank Drake presented in 1987. And I was just a newcomer that, just fascinated by SETI. So I dared to talk with Professor Drake, and they said, I'm honored to meet you, and I am a newcomer. And they said, you are a newcomer? Yes. Okay. And then he spoke with me about this concept of the gravitational lens. So in conclusion, what I am presenting today, that is the book that you see here, is the result of 20 years of thoughts and calculations about this space mission that Frank Drake put in my mind and is still there, actually. Okay. So I am sorry that the cost of the book is so high. It's $140 in the US. And this is because publishers, of course, can decide about the cost of books. This is a technical book. Unfortunately, this is not a popular book. I would have difficulties, I have to admit, to write a popular book because English is not my mother tongue, so I don't know all the subtle ways to capture the attention of readers, in a charming way. Here we have Seth Shosta, who does that much better than I can possibly imagine. So someone else will have to write the popular version of what I'm talking about. And this, unfortunately, is a mathematical treatise, basically, or physical-mathematical treatise. And this is why it costs so much. Let me please show you the book cover, and let me tell you more about this, because this is, the picture down here is really showing the idea in a visual fashion. But of course we would need artists to give us more artist concept about all this. So this is just a preliminary vision of the story. Sorry. Okay, let me go back. So this is the previous part enlarged. And you see that this plane here represents, so as to say, the plane where the space mission is taking place. Now, at infinity, that is at the horizon, we have this bright light, meaning that over there at infinity, or anyway at a very large distance from the sun, there is an intense source of radio waves. Now, what could that possibly be? It could be, if you are a cosmologist, an object at the edge of the universe, like a quasar, that are well known to throw out an awful lot of radio waves. But if you are not a cosmologist and you are rather a SETI scientist, that could be an extraterrestrial civilization sending out signals. Why not? From the physical point of view, this is practically the same, because both the quasar and the extraterrestrial would send radio waves, as indeed we do, because the Earth is throwing out an awful lot of radio waves, especially the military radars. So we are already doing so right now, inadvertently if you wish, but this is what is going on. So over there is the source of radio waves. Now, the radio waves travel, and these are basically parallel lines, until they reach the vicinity of the sun. This is the sun. And you see that actually it was depicted in a little lower level with respect to the plane, because this is to mean the gravitational well of the sun. So this is why the sun is slightly lower than the plane, right? Just to let you understand that gravity is around there. And of course, this gravitational well is bending the trajectories of light rays, and so this is why you can see these curves here. And since the light rays are made to bend, then they must focus on the other side. There is no way. And this is where they focus. So this point here, where they focus, can be correctly called the focus of the gravitational lens of the sun. So far, so good. I guess that everything is clear. But then I have to tell you the big news, which is also a big difficulty for a real space mission. Well, when you go over through all the calculation in general relativity, then you find that this focal point is actually distant from the sun 550 astronomical units. Now, this is a big number for space missions. Just imagine that the orbit of Pluto from the sun is about 40 astronomical units. So, you know, it's far out. But there is no way to do the same mission closer, because it is easy to prove, and in a moment I will prove it more serious way, that if you just keep staying closer to the sun, you get nothing, because you are in the shade of the body of the sun itself. Okay, so this is the minimal focal distance. And actually, it can be proven that all points along the straight line coming from the source and passing through the center of the sun and going beyond this minimal 550 AU distance, all points along this light, and actually in this area here, brighter area, are focuses of the sun gravitational lens. So here we find something, quotes, unexpected from the intuitive point of view. Because what we are used to consider in classical physics, that is in classical optics in this case, is that classical optics, like the glasses that we use, only have a very well-defined focal distance. And your eye must be exactly on that point to see well. Now, this is not the case for the sun, because it can be proven that any point from 550 AU onward, theoretically up to infinity, is indeed a focal point. So this is not a focal point in the traditional sense. It is actually a focal straight line, starting from 550 and going over to infinity. So here is the first novelty in the story, but many more will come along, okay? Now, these things that you see down here is the spacecraft that I call focal spacecraft, because the whole mission seems to me to be correctly called focal space mission. Now, of course, when a spacecraft is going to be designed, there are usually discussions among the designers. You know, as it was said in my introduction, I spent 20 years of my life at a space company in my town is Torino, where the Shroud of Turin is Turin in English. And I spent 20 years there at a space company called Alenia Spazio, where I came to conceive this space mission. And actually, I have to say that by the year 2000, I submitted a formal, official proposal to the European Space Agency, ESA, in order to have this mission considered for possible fundings. Now, sorry to disappoint you, they did not fund my mission, but nevertheless, the file is there. So I have to be frank, one of the reasons why I am here in the United States is also to consider a possible resubmission of this proposal, probably in a better form, to NASA, to have NASA consider the first, quote, interstellar or precursor interstellar mission that would be different from all space missions done so far. Because all space missions done so far were just, at best, for the exploration of the solar system. But this goes far out, much out of the solar system. So this is the spacecraft as I could possibly imagine that. And you see two big antennas tied to each other by this sort of string that in the space jargon is called a tether. Now, the basic idea, I'm sorry, I'm using the gesture, you know, the Italians like to use the hands all the time, so please forgive me. But the basic idea is that these two antennas would revolve in this way around the center. So this is the real spacecraft. It is very small. But the two antennas revolve in the orthogonal plane to the direction of exit from the solar system. And this is done with a precise purpose, that is in order to allow interferometry to be done, which is one step ahead in order to get better angular resolution and better seeing, so as to say, of the whole lot on the other side. Okay, so this is the intuitive description of the story. And now let me please repeat very shortly the same story in a more scientific way. So once again, imagine please that on your left at infinity is the radio source, whatever it is, an extraterrestrial civilization, a quasar, radio galaxy, bright star, whatever. So the waves arrive parallel, but when they get close to the sun, they are bent by the mass of the sun. And the equation that is giving you the bending is this. So if you call by alpha of r the bending angle, that is this angle over here, the value of this angle is not the same for all rays, but it depends critically on the distance r from the center of the sun. And this is precisely why these two rays are, you know, have a steeper inclination with respect to the axis, whereas this one has a smaller inclination. Sorry. And if I keep going to infinity, so if I put my spacecraft up to infinity, of course, in the end, they would be parallel. There would be no inclination at all. So this is the critical point. And you can now realize immediately why there is this minimal focal distance. This is the 550 AU point, and you cannot get anything at closer distances because the sun is blocking the propagation of waves. So waves, radio waves, cannot go through the sun. They are stopped by the sun. Incidentally, here I'm just going to say a very brief sentence for people versed in general relativity, you know, physics. If we are talking about gravitational waves, that is, the waves of gravity predicted by general relativity, the story is different because gravitational waves can cross through the sun. So the focus for gravitational waves is much closer than 550 AU, and actually it turns out to be in between within the solar system and between the orbits of Uranus and Neptune. But that's another story because you need a gravitational wave detector. So I'm not going to discuss this in this presentation. Okay, next. I told you about this deflection angle, and let me tell you something from the history of the point. From the point of view of the history of science. Now, this is a remarkable year, 1907, when Einstein realized that his theory of gravity yielded a factor of 4 here in the deflection angle. This is important because if you stick to the older theory of gravity, Newtonian theory of gravity, you get here only a 2. Now, what does that mean? It means that the bending angle for Einstein is twice as much as the bending angle for Newton. And so the distance that we have to reach for Einstein is half as much as the distance that we should reach according to Newton. So we should really say thank you, Professor Einstein, because you have half the distance and you have made our mission possible. Certainly much better than what Newton would have said. Next, this is just what I meant. These are the masses of the sun, radius, sun density, Schwarzschild. Look, I know that in America some person pronounces Schwarzschild or something like that. He was German, and I am from Europe, so if you don't mind, it's Karl Schwarzschild, as they say in German. Anyway, he found the first exact solution to the Einstein field equation. And the Schwarzschild radius is basically the radius of a black hole. That is, if you could put the whole mass of the sun inside the Schwarzschild radius, which is only about 3 kilometers for the sun, so you would have to compress things really a lot. But then if you could do that, that would be the radius of the black hole having the same mass as the sun. Okay, next. Oh, here we go over to poetry, if you let me use this term. Now, this beautiful set of sentences that I'm not going to read was written by Professor Frank Drake, and I'm sorry that he is not here. I met him 2 days ago. Anyway, this was written by Professor Frank Drake in the preface, or forward that he wrote to my book years ago. And basically, he describes the novelty of the fact that every star is a gravitational lens, of course, because it bends space-time around itself. Now, Frank Drake is pointing out that each civilization, and if there are civilizations more advanced than us, probably they realized that a long time ago already, each civilization may, and actually has to, take advantage of this, because it can be proven that if you use 2 stars as magnifying lenses for radio communications, practically speaking, you can communicate from one stellar system to another one with much lower powers in the game than if you just communicate by virtue of ordinary antennas that humans do. But this is trivial, because there is no comparison between the size of the antennas that humans have built so far and the size of the sun. So it's like using the sun or any similar star as a big antenna. And this is precisely what is needed across vast distances as we have in the galaxy and outside. So I'm not going to describe all this. Incidentally, I leave the presentation, and probably this will be put on the website of the SETI Institute, so you can retrieve all this later, so there is no time. Anyway, this is a beautiful description, because Frank was the person who suggested to me all these. Sorry. No, I'm sorry, I'm going to, no, sorry, just a moment. Frank suggested to me all these, and oh gosh, where am I going? No, that's too much. So yeah, sorry about that. No, but look, can you take me the, sorry about that. Okay, so that was the poetic part of the story. Now let me give you more technical details and also start looking back, please. This is still back. Excellent, perfect. Now, these slides only points out what I said already, that is, there is an infinity of focuses starting at 550 U and going over to infinity along this axis, that is the source, center of the sun, position of the spacecraft. Period. This is obvious. But then we start facing many problems. I just mentioned one. Well, the fact that we don't have to stop the spacecraft at 550 U is wonderful, excellent. It would have been extremely costly for us to stop a spacecraft just there. This is not the case. Second, the farther it goes beyond 550 U, the better it is, because, as you remember from the previous diagram, the corresponding radio waves are passing at a higher distance from the center of the sun. Now, in practical terms, this means that they are not being hit, or less hit anyway, by the flames that, of course, distort the radio waves. So here we are stumbling into a really big difficulty, that is, quotes in easy terms, the theory of the flames, which in scientific terms is called the theory of the solar corona. Now, the sun is not a spherical ball without flames. There are flames. So we have to take this into account. And so there are 2 chapters in my book that are actually considering the mathematical theory of the corona as it was done by JPL experts and I about 10 years ago. And this is the best thing that we can have at the moment. But I'm sure that better model might be found by some young, bright person, and we terribly need that. Okay, next. Gain of a star. Now, here is the key point. Let me explain this in easy term, and then I go over to the equations. In easy term, the idea is that we use the sun as a radio antenna. Okay? In other words, it is as if we had an antenna as big as the sun, and of course this is wonderfully helpful for the telecommunication. Now, radio scientists and radio astronomers, and of course SETI astronomers, use the notion of gain, which is this capital G, and this applies to any star, not just to the star. Basically, the idea is the gain is the focusing capability of the antenna. In other words, if you just have no antenna and you emit, the waves propagate in all directions. This is the worst case because you're wasting an awful lot of energy in all directions. But if you want to have a beam, then you have a sort of paraboloid or any other shape that is focusing the beam in a certain direction. Now, how much focusing is achieved is actually expressed by this notion of gain. So this is what I understand by gain. It's a geometric focusing concept. Now, it can be proven, but this is not an easy proof at all, I have to confess, that the gain, the radio gain in some sense of any star at a wavelength lambda is given by, is given by this factor 4 pi squared times Rg, that is the Schwarzschild radius or gravitational radius of the star, over lambda. Okay? This is the great result. I repeat, this is not an easy thing to prove. You have to go through electromagnetic theory, merge this with general relativity, and then you find the result. Even more. Now, let me express in easy terms how wide or how narrow the beam must be. Well, the point is this one. If you define a variable rho, which expresses the distance where you are, where your point is, with respect to the axis, with respect to the focal axis, then you have the first part, which is exactly the same as in the previous formula, that is 4 pi squared times the Schwarzschild radius over lambda, but multiplied by this factor, which in physics is called the Bessel function of order 0, and is a typical pattern of radio communication. That is the antenna diagrams, even in ordinary antenna grant theory, are expressed in terms of this thing, the Bessel function. So anyway, this gives you how much the intensity, that is the gain, decreases when you go off axis. And here I have to give you bad news. That is, the alignment in between the source, the center of the sun, and the spacecraft antenna must be extremely strict. Just to quantify, something of the order of 100 meters. So this is terribly bad. I know. We were debating this point, of course, at JPL when discussing the so-called NASA interstellar probe. And let me tell you what they asked me. They said, what? Are you asking to track the spacecraft with the precision of 100 meters at the distance of 550 AU? And I said, yes. Well, that's impossible. I would save you other words. Okay, but this was basically the meaning. And they are absolutely correct. Well, I will tell you later how I could possibly answer this question. But this is certainly a very high difficulty. The alignment is very strict indeed. Final line, the bottom line. Well, if you have a system, space system, that is made by more than one antenna, so far we have been speaking only about the antenna of the sun, but not about other antennas. But this is not the case, because as you remember, we need the spacecraft to pick up what is focused there. So in the game, we have two antennas playing, the sun antenna, but also the spacecraft antenna, okay? Now, it can be proven that the overall gain, that is the gain of the full system, is made up by the multiplication of the two gains. So you multiply the gain of the star times the gain of the antenna. And this is the same story. I'm not going through there much more. Good. So far about the space mission, the electromagnetic aspects, and so on. But now let me please extend our scenario, as we say in it. Now, there are a few scientists, not really many, but a few, that are considering future space missions. And the dream, of course, is to get to the nearest star. Nobody knows how to get there at the moment, because the propulsion system, the propulsion problem is terrible. Nobody knows how to face that. Incidentally, may I suggest that you have a look on your website at a website called Centauri Dreams. Is anyone familiar with this? Okay, some are. Good, thank you. Now, if you please have a look at this website, which is written by a journalist called Paul Gilster. He describes in a perfectly understandable way what the scientists would describe with technical papers. Essentially, the point is this one. We do not know how to get to the nearest stars. And here is where my proposal comes out. The problem, of course, is that even the nearest stars, Alpha Centauri, which is a triple star system, is so far away that we cannot get there. We do not know how to get there. But my proposal is not to get there first. My proposal is that the sun focus comes first, and then the real interstellar target comes second. So my proposal is to send just a mission to the sun gravity focus, which is, of course, much closer. How much closer? Well, roughly speaking, 253 times for Alpha Centauri, but of course it is much, much closer for any other star system, because the stars are far away. So here is the real possibility for making this space mission become reality in our days, not in the far future. It would be possible to set up a space mission like that. It doesn't require anything special. You just need a large antenna on board, and of course you need a propulsion system capable of taking you to 550U. But 550U is not as far away as Alpha Centauri, not to mention any other star. So this is what I think my proposal is new with respect to other proposals. Now, I hope you'll forgive me if I make a comment about the United States, which is the country that is hosting me that I love. But but let me say, it seems here that all the people are so much impressed with Star Trek that they all want to go faster than light. Go faster than light. But faster than light is not possible at the moment. I'm not ruling out that in 100 years, or even less, it will be possible. For instance, I'm thinking about quantum entanglement, which is a very promising field. But all this, at the moment, is still in the minds of top theoretical physicists, not in the physical realities of space companies. Whereas this stuff is within the possibility of space companies. So I'm not talking about too far future, I'm talking about present day. Good. Now, just to mention another problem, this is a very complicated mathematical problem. Let me just mention to you what the spirit of the story is. And incidentally, this would be an excellent theme for PhD students who have to write PhD theses, and they want to show up that they know mathematics better than the teachers, which is hopefully the case. But anyway, so the story is this one. Consider, for instance, that we want to go opposite to the Alpha Centauri system, okay? In other words, if we want to get radio images very largely magnified of the Alpha Centauri system, then we have to send our focus spacecraft exactly in the opposite direction with respect to the sun, obviously. Now, if you look at the declination, that is the latitude, of Alpha Centauri, this is minus 60 degrees. That is, Alpha Centauri is in the southern hemisphere. It is not visible from here. And you have to go down, with respect to the equator, minus 60s. Now, this means that our spacecraft has to go up 60 degrees in the opposite direction. Agreed? Now, this is bad news for the engineers designing the space mission, because people in the space business know that any, as they say, inclination change that is changing the trajectory with respect to the ecliptic by an angle of 60 degrees is terribly demanding in terms of fuel. So once again, if I was going to ask the engineers to design a space mission getting out of the ecliptic plane by an angle of 60 degrees, they would say, oh my, you know, this is too bad. So once again, we have a problem. Now let me tell you how this problem could possibly be faced. Well, the solution is here. Again, the largest mass in the solar system is the sun. If you imagine to approach the sun from below at a suitable distance, so you have to compute that, the sun would let the spacecraft exit along an hyperbolic orbit with the focus at the sun, and the sun would give you for free any inclination change you may possibly need. In other words, you can design the trajectory, but the last flyby of many as you wish must be the sun flyby, because this is the only flyby that gives you free inclination, no fuel at all. Now, this is very good, but it has an opposite side. That is, how close to the sun do you have to fly? And if you fly too close, you know, it may be very hot over there. So this is risky. Now, we could change, and rather than using the sun for that, we could use Jupiter, which is the second largest mass in the solar system. This was indeed used already in a space mission by the European Space Agency called Ulysses. People familiar with that know that Ulysses went out of the ecliptic plane after flybying Jupiter. So this was done already. We could do it. It's up to us to decide, you know, of course, then there are the flight times involved. So it's a very complicated mathematical problem that you know, I am too old to face. Okay, so the message is for the young guys. Then let me say something about the solar corona. Now, anybody interested can read this paper down here by John West of JPL, published in Acta Astronautica in '99. Essentially, in my book, there are two chapters. Incidentally, here is the book. If anyone would like to have a look at the end of the talk, here is the book. So in my book, there are two chapters devoted to this. And essentially, let me come straight to the point. This is the key diagram in the full story of the solar corona. Now, let me tell you how to read this diagram, please. On the horizontal axis, you have the distances from above the surface of the sun in units of the sun radius. So this first one that you see here means one sun radius, which is the surface of the sun. Okay? And then you go over to 1.05 and so on up to 1.4. Actually, we could go over to 2 because the solar corona, that is the flames, extend roughly up to 2 sun radii from the sun. Now, on the vertical axis here, you have the real focal distances that the spacecraft has to reach in order to find the real focus. Now, you say, but you said that the real focus is 550 AU. Well, I'm sorry to disappoint you again. This is true. That would be true if there were no electrons in the solar corona. But actually, in the lower stratification of the solar corona, there are a number of free electrons. And they are doing exactly the opposite of what we want. That is, if the gravity is focusing our radio waves, the electrons are doing the other way thing. That is, they are defocusing, they are diverging. It's a divergent lens, the one created by the electrons in the corona, not a convergent lens. So in other words, there is a fight in between the gravitation that wants to focus and the electrons in the corona that wants to have the divergence. So the conclusion is that it depends on the frequency that you are observing And the real conclusion is that the real focus is pushed out from 550 AU to higher distances according to the frequency that you are observing. Okay? So this is the bad effect of the corona, but we cannot do anything else than face it. Now, on the vertical axis, there is this real focus. You see that it starts at 550 AU in AU, of course, and it goes up to 1100 AUs. Now, these curves here are the curves of the real focal distance according to different frequencies. For instance, the first, this one, is for a frequency of 59 gigahertz. The second, this one here, from above, is for a frequency of 122 gigahertz. And here is the most important one, the red one, this one here. The red curves goes, the red one here, goes on the frequency of the peak of the cosmic microwave background. And this is precisely what I would suggest to observe in the first focal space mission. So let me please open up a small parenthesis, but I have to explain this. Now, we all know that the universe is filled with this relic of the Big Bang called the cosmic microwave background. Now, the spectrum of this thing is a perfect Planck curve, that is the black body radiation curve, for a temperature of 2.7 Kelvin degrees. We all know about that. Nobel laureates discovered that, Penzias and Wilson in the 1964, and then many other space missions have been built to observe the inhomogeneities in the cosmic microwave background. I'm just thinking of COBE, the American mission COBE, and then the next mission WMAP, and then the European mission Planck. Okay? So they are all doing the same thing, but the difference is that the angular resolution in observing the CMB is improving in time. Now, if you go over and compute the peak of the microwave background, you find that this is about 360 gigahertz, which corresponds to this curve in our diagram. Now, please look at this point. This point means that the real focus is above 750 AU. And actually, the computer gives me 763 AU. So, in other words still, if we want to please the cosmologist and use the focal space mission in order to look at the cosmic microwave background with a huge angular resolution, much better than anything we can do humans because we are two small guys, then we must reach 763 AU and not just 550. Period. Is that clear? So, honestly, I would propose in any space mission to try to reach that distance. It will be reached anyway. It's just a matter to wait 20 more years. These are the distances in the game, and there is nothing we can do about that. So anyway, I wanted to point this out. And if you look at the distance from the center of the sun where these waves are passing, you find 1.1. So they are above the sun surface, but not too far. So the effect of the corona is unfortunately remarkable. What to do about that? Well, here is one suggestion, but of course there may be other suggestions. My suggestion was to have a spacecraft that is actually doing interferometry. I told you already about that, so I suggested to use two antennas that revolve around the real spacecraft, which is this little thing in there, and they are tied to each other by a tether. And this is precisely what you would see. You see, you have antenna number one here, so it's a dish. In my calculation, this was a 12-meter dish, but we can improve it. I mean, it's up to the engineers to decide about that. This would be the second antenna. This is the focal spacecraft. This is the tether on one side. This is the tether on the other side. And of course, you release slowly the tether. And so they move, not in a circle, but in a spiral. And this is called Archimedean spiral because apparently the first mathematician who found the equation of the spiral was no less than Archimedes in Greek Roman times. So these are two Archimedean spiral, and practically speaking, what you get is that they move around in this way, and they cover a much larger field of view than if you had only one antenna. So this is very good news. And this is precisely the technique that radio astronomers do, VLBI and synthesis, aperture synthesis radio astronomers. So we all know about how to handle that. The point is just to increase the tether length or decrease the tether length. Okay, next. Now, I would like to suggest to you 3 different targets for this space mission. One is the galactic black hole. One is the triple star Alpha Centauri. And the third target may be any extrasolar planet. For instance, I selected Gliese 581, but it could be anyone. Let me go over to the details so you see how the spacecraft and the full mission is different according to the target you want to observe. So let's start with the galactic black hole. Now, the good news is that in recent years, as you certainly know, the last 15 years, a lot of research has been done about the monster that is located at the center of the galaxy. Why monster? Because this black hole appears to have a mass, now they say 4 million times the mass of the sun. So it is a monster. How can you possibly imagine such a massive object? And yet our galaxy is a quiet one. So there is much worse probably in other galaxies, but this is their job, not our job. So anyway, just imagine please this. Now, here is the sun. I used the old value of 32,000 light years because when I was a student, they taught me that this was the right value in between the center of the galaxy and the sun. Now they say this is 25,000. Sorry, but doesn't change too much the story. Anyway, it does only change slightly the story. Now, here you have this monster, the galactic black hole. Of course, this is a sphere. And please imagine that this thing, this Archimedean spiral, are taking place in the perpendicular plane. I couldn't draw it in a perpendicular way, but you have to imagine that. And you also have to imagine that all this thing is exactly the same, but in the perpendicular plane, okay? So this is precisely the trick that I am suggesting. We have the spacecraft, our spacecraft, going up to 550 AU or more, according to the frequency you want to observe. And then you have these 2 tether antennas that are tied to each other by a tether, but the tether is deployed so that they move along spirals. And of course, they cover a much larger field of view on the other side. So the conclusion is that there is a trivial calculation that I now just show you. You can write from the similarity of the 2 triangles this proportion. Minimal tether length is proportional to 550 AU as twice the Schwarzschild radius of the galactic black hole, which is the diameter of the black hole, is proportional to 32,000 light years or 25,000, whatever you want. So in this equation, you only have one unknown, which is the tether length. All the rest is known. So you solve for that, and you find what the tether length is for a spacecraft going to watch at the galactic center. And the result is wonderful. It's less than 2 kilometers. Now, everybody in the space business knows that this is absolutely feasible right now. We already flew around the Earth, tethers up to 18 kilometers or even more. So this is technologically within today's reach, which is what I'm stressing, because it makes the space mission becoming real and not faster than light stuff. Okay, so this is what I suggest for observing the galactic center. Now, let's change the target. Let's go for Alpha Centauri system. Why Alpha Centauri? Well, obviously, because when the time will come when we really can fly to the nearest star, it's out of the question that Alpha Centauri will be the first target, because it is the closest star, and that's it. So what can we do now? Well, the first thing is that we should just fly in the opposite direction, as I said, reach the focus of the sun, and have a very highly detailed radio picture of whatever is in the Alpha Centauri system. For instance, today, there is a strong research effort going on to find out whether in the Alpha Centauri system there are or not planets. So far, no planet has been discovered, but who knows? They could be there. They could be small. So we didn't see them so far. Okay, so this is a big question mark. Now, certainly, by using these, we would be able to find out whatever is in the system, because we have such a magnification provided by the sun. Now, let me just tell you that if you try to apply the same trick of, you know, these two revolving antennas and the tether and so on for Alpha Centauri, I'm sorry. No way, because the length of the tether would be 10 to the 6 kilometers. So 1 million kilometers. So this is crazy. We cannot have any tether like that. So this is to say that we cannot use that trick in order to watch at the Alpha Centauri system. Obviously, because the Alpha Centauri is much closer than the center of the galaxy. This is what plays in the game. So we must use something else. Now, this is a picture of the Guggenheim Museum in New York. But I tilted the picture in order to let you have an intuitive description of what a conical helix is. Well, a conical helix, as the name says, is a helix. That is, it goes up like this with increasing radius. But it is located on the surface of a cone. Okay? So you start from one point, which is the apex of the cone, and then you keep increasing that. This is a conical helix. Now, why do we have to think about the conical helix? No, I'm sorry. Because this is the only way to have our spacecraft going around the focal axis between ourselves and Alpha Centauri and get a larger field of view of the full system by changing the trajectory rather than by using the tether trick. Okay? Now this is demanding because it's not an easy thing to have a spacecraft moving along a conical helix. So people in the space business will have to think hard about how to get that into reality. But honestly, this is the only solution that they could possibly imagine, because the field of view for Alpha Centauri is so large that we cannot do it by other techniques. Final point, just one extrasolar planet, for instance, Gliese, whatever. Well, here the story is another one. Extrasolar planets are not as close to the Earth as Alpha Centauri. They are farther out, but certainly not as far out as the center of the galaxy. So we have to devise techniques that somehow are halfway in between the two ones that I described. Let me just give you one thing. My suggestion is to watch at these planets on high frequencies, because essentially that formula over there gives you the linear resolution provided by the sun gravitational lens. And so if you want to see the details of these extrasolar planets, we should go for highest frequency as possible. Sorry, that's all I can say. I'm sure that much more could be possibly said, but that's all I can say. Good. Now, let me tell you about some real proposals, starting with NASA. Now, about 10 years ago, a group was assembled at JPL to study a mission called the NASA ISP, Interstellar Probe. And I was one of the persons in the team. Now, here the story is completely different. That is, the sun, as we know, is moving around the center of the galaxy. And it takes 200 million years to make a full turn. But the sun emits its own wind, which is actually a flux of protons, called the solar wind. So there is a region around the sun in the shape, let me say, of a comet. So it has a small nose here and an awfully long tail on the other side. But there is a region in space around the sun where the solar wind is predominant with respect to the interstellar wind, which is the same story as the solar wind, but coming from other stars. Okay? And the frontier surface in between the solar wind-dominated part and the interstellar wind-dominated part is called the heliopause. Now, the idea of the JPL people in designing this space mission is, let's send the spacecraft in this direction. So let's send the spacecraft into the direction of the nose of the heliopause. The nose is where the heliopause is closer to the sun, okay? so that we get there with the minimum amount of time, obviously. This is the key point. Now, if you want to know the numbers, roughly the theory predicts that the nose is about 141 AU, so much closer than 550, which is why the JPL people consider the missions. And they completely agree with them. The only point that they suggested in this study was that since the spacecraft is going on after 141 AU up to any distance, so sooner or later it will also get to 550, then please be prepared and put aboard the spacecraft something that when the spacecraft gets to the focus, tells us that it has reached the focus. So this could be a magnetometer, could be a bolometer. We can discuss about that. This is engineering stuff. But the point I made during this study was that we should put something, because this is not stopping at the heliopause, it's keeping going. And sooner or later it will prove to us that this is the actual focal distance and not just what we computed. So far we only could do theory, mathematics, and not real stuff, not actual experiments, okay? So this is the basic idea of the interstellar, NASA interstellar probe. And you know, if I will ever be allowed to submit a proposal to NASA or to any other space agency, I would certainly suggest to continue the work there, because much of the work is done already. And then there is another advantage. But let me also tell you for the moment that also the European Space Agency has done the same thing. So this proposal by the German Wimmer Schweingruber, associated with Ralph McNutt of APL, Applied Physics Lab at Johns Hopkins University, is the same as the NASA proposal, basically. Okay, now here again is the same story. So you have the solar system, this is the orbit of Pluto, and so on, and so we get this way. But now I wanted to point out the second advantage, apart from the what I said already. And this is the second advantage. Now, these two plots show you all over the celestial sphere which is the direction of the incoming interstellar wind. In other words, we are at the center of the celestial sphere. Towards us, because of the motion of the sun around the center of the galaxy, we have a flux of hydrogen, helium, oxygen, and other things, which, roughly speaking, all come from the nose of the heliosphere. Now, here is an extremely lucky circumstance, meaning that we were just lucky and nothing else. There is no relationship, physically speaking, with these parameters. That is, this nose is really very close to the ecliptic plane. But this is just by chance, because of course the ecliptic plane depends on how the sun was born 4.5 billion years ago, whereas this stuff, the interstellar wind, is a completely different story. But we are lucky, because the nose is actually just a few degrees away from the ecliptic. And this saves us from changing the inclination of the spacecraft with a large angle, which is exactly what propulsion engineers in space business want, because then it would have been much demanding in terms of fuel. So here is one more reason to adopt this target for the mission to the gravitational lens of the sun, because it is not so expensive in terms of fuel consumption. But here is the final point in the story. Let me please tell you. I told you already that the cosmic microwave background, CMB, is extremely important for cosmology, because it's the remnant of the Big Bang. And you know, we have spent already 3 space missions, 2 Americans and 1 European, to watch at the cosmic microwave background with the highest possible resolution. Okay, now in my book it's written that if you use the sun as a magnifying tool, oh my, then you get such a huge resolution that by far dwarfs all the previous space missions, because you have the sun in between. So this gives you an enormously higher resolution. Roughly speaking, I computed that the increase would be of the order of 1 billion times. Now, this I am going to use as a lever, the Archimedean lever, to convince the cosmologists that this is serious stuff. Why the cosmologists? Well, let me speak in political terms, because in the end, science is all nice, but in the end, it comes to the politics. Now, the community of cosmologists is extremely powerful in the astronomical world. Really, they are practically suggesting space mission like the ones I mentioned, COBE and WMAP and Planck in Europe, that cost a lot of money. And the European and NASA agencies are putting money because the cosmologists ask them to put so. So if the cosmologists come to realize that using the sun as a gravitational lens would give them 1 billion times better angular resolution than all the previous space missions, I guess that they would go for that. And this would also help us, poor SETI scientists, who have a hard life because many people don't regard SETI as a serious stuff and so on and so forth. So this is the political trick, to be tried in order to have the support of a larger community than just the SETI scientists. Good. So all this is described in the book, and what I'm talking about is are the two final chapters of my book, and the first part. Now, let me come straight to the point. The second half of the book is devoted to a completely different story. It's not as nice, physically speaking, as the gravitational lens of the sun. This is another story. This is a mathematical description of an algorithm that would pick up very weak signals out of the background noise better than the Fourier transform, FFT, that is the standard tool that the whole world uses, including the SETI world. Now look, I know that it's pretty late, and I mean, I really used much of my time to describe the sun gravitational lens because this is so much more romantic than mathematics. But now, here is the second part, and I am sorry, it is terribly mathematical. If you give me 10 more minutes, I would go. So let's be democratic. Would you mind if I speak for 10 more minutes about that, just summarizing the story? Okay, this is mathematical, I say, but I'll try to be clear. Now, what is the KLT? First of all, what is the K and what is the L? Well, the K is the initial of a Finnish mathematician, Kari Karunen. And the L is the name of a French-American mathematician, Michel Loève, who came over here at Berkeley, and I guess his wife is still, his widow, I'm sorry, is still at Berkeley. Anyway, there is a Loève Prize at Berkeley for young people dealing with probability things. So what is the KLT? The KLT is named after these two gentlemen who discovered the full mathematical stuff in 1946. But let me explain things in a very easy fashion. Forget for a moment about all this mathematics and just consider an object. For instance, this book, Newtonian physics. So there is nothing easier than that and more intuitive than this book. Now, this book has its own mass. And in Newtonian physics, I can use a system of free axes x, y, and z to describe this book in terms of Newtonian mass. However, because of the shape of the book, which looks very much like a rectangle or something like that, there are 3 directions, 1, 2, and 3, that are privileged with respect to any other direction. Agreed? Now, these privileged directions are called by mathematicians and scientists principal axis, or inertia axis, and so on. And the basic idea is that if you change the reference frame, so here you have your book, and initially your reference frame was here, but if you change it and you bring it exactly in the 3 privileged direction, your mathematical description is much simplified. Or in mathematical terms, 3 times 3 matrix becomes 0 everywhere except for the 3 terms on the main diagonal. That's all. Now, this stuff was discovered in 1748 by Leonhard Euler, the Swiss mathematician. And this is precisely what happens. Now, if you pay just a moment attention to this matrix, this is the 3 times 3 inertia matrix that describes in Newtonian terms everything. After the principal axis transformation, you have all zeros except for the main diagonal. So this is called the principal component analysis or principal axis transformation. There are many names for that, but this is the very simple idea. Now, these axes are called eigenvectors, which is a name coming from the German. Eigens mean proper, essentially. So you could call them proper vectors. In other words, each body, each of us, has his own eigenvectors or her own eigenvectors. That is, the vectors describing the masses of the body in the best position. And they can be found mathematically. You just need a good computer and something else. Now, the idea of the KLT is simply to pick up all that knowledge from Newtonian stuff and to translate that into signal processing, that is the theory of getting a signal out of the background noise, by assuming that you can expand these things here, which is a random function of the time, that is, you have the time axis going that way, and you have the y-axis going up and down in a random fashion that you cannot predict. So it's not an analytical curve, it's a random thing. And in the physical real world, this means that you call by that thing, capital X of t, there is a name, stochastic process. But essentially, in physics, this means that this is whatever comes inside your antenna. In other words, you have a big radio telescope, as here in the SETI business. Basically, what comes inside your radio telescope is noise, that is, random fluctuation. But there might be a signal buried in the noise, much tiny, much less intense than the noise. So what you do is to pick up whatever comes inside. I don't care what is that, everything. And I call this a stochastic process or random input. But then, well, random input over a finite time span. So the time ranges from 0 to capital T. Now, incidentally, this story of the final time span is important for mathematicians, because in the Fourier transform, unfortunately, you have to confine yourself to infinite time span, or nearly so. So this creates an extra number of mathematical complications. This does not exist in the KLT from the very beginning. Anyway, you pick up that, and then you try to describe that as a sum, an infinite sum. You see this sum ranges from 1 to infinity of terms. And each term is, in loose terms, statistically independent from the next neighbor. It is like a town. Everybody has his own apartment and does what he or she pleases. Okay? I am statistically independent from anyone else, in theory, but this is the case. So each term is statistical independence. Not just that. Each term is actually achieving a decomposition. That is, this capital Z represents a random variables. That is a probability distribution that is fixed in time. Whereas the function of t, phi of t, is a pure time function, which is not related to probability. So in other words, this is a subtle way to say that I have decomposed my random function in the statistical part and in the time behavior from the very beginning. Again, this is a new thing with respect to Fourier. It's completely different. Now, I don't want to harass you too much, but essentially, in Fourier, you have these conditions, which means that the functions on which you expand your signal, that are sines and cosines in Fourier, are orthogonal to each other. Orthogonal in the mathematical sense, that is the integral of the product of two equals 0 or 1 if for the same variable. This is the key point in the story, and it was discovered by, again, the Swiss guy, Leonhard Euler, around 1748. And it was after this discovery that Fourier realized, Fourier was a French guy who lived later, 50 years later, he realized that he could use the Euler formula, which is just this, but for sines and cosine, in order to reconstruct the coefficient in the series by performing the so-called inversion. So historically speaking, this was an important step ahead. Now, let me just come straight to the point. The same story applies to the KLT, and here it is, but with one more complication. That is, in the KLT, I use a second orthogonality. That is, not just one, as in Fourier, Euler, and so on, but the second one that applies to the random variable here in the sense of probability. And this means that the autocorrelation, this is what it is, the mean value of the product, is 0 for different random variable, But it cannot be 0 for the same random variable, otherwise that random variable would be 0. So this lambda here, which is called an eigenvalue in the language of physicists, is actually the variance of the random variable. So let me put that in an easy way. The easy is this thing, that the KLT is much more profound mathematics. First of all, because it uses 2 orthogonalities, not 1. But then there is one more point that I have to stress. The good old Fourier stuff relies on the idea that the only basis function, that is the only set of axes on which I perform my expansions, are sines and cosines, period. Here, we do not make any assumptions on that. From the very beginning, we don't know what is the set of basis function. But we discover that along the solution of the problem, because it can be proven, and this is the next slide, that the basis functions, that is the eigenfunctions, are the solution of this thing, which is an integral equation, where the autocorrelation is the known part, and the functions and the eigenvalues are the unknown part. So here is the most profound aspect of the story, because you are not tying yourself to a specific set of functions on which you expand. You discover which one is the best set according to the different problem you solve. So this means that the transform is really adaptable to different problems, completely different problems. So after the discovery of all this stuff, there were cases where mathematicians and physicists and engineers and so on could solve the integral equation. Let me please tell you that when I was a PhD student in mathematics, I got my PhD because I was able to solve the integral equation for a special class of functions, which are so-called white noise integrals or time scaled Gaussian processes. I know this is technical, but anyway, the conclusion is that for that particular class, the eigenfunctions are Bessel functions of the first kind. And they are not sines and cosines. They are different animals, okay? And the eigenvalues, the lambda n, for that case, are the zeros, that is the point where the function is 0, of central-linear combination of the Bessel function and their first derivatives. So anyway, in conclusion, the KLT adapts itself to the problem that you are considering. And in this sense, it is capable of recovering out of the background noise a signal that comes inside your radio telescope with a much lower signal-to-noise ratio than Fourier. And this is precisely why the SETI Institute people, and especially Jill Tarter and Frank Drake, and I'm grateful to them because they realized this. This is not an easy thing to realize in the beginning for people trained with classical stuff, you know. But when you realize the much more wide vision that this can give you, then you are ready to pay for the extra computational burden that your computer has to face in order to find out the eigenvectors and the eigenvalues and eigenvectors. So the conclusion is that there is a group of people here at the SETI Institute, led by Jill Tarter and Frank Drake and so on, that would like to put this algorithm on the Allen telescope array, because we do not know what the hell of the signal the extraterrestrial might send us. Now, this is an important point, because in other applications, all this, the KLT, can be easily bypassed by the so-called match filter. Now, the match filter is essentially something that gives you the best filter to filter out anything if you know what the shape of the incoming signal is. And this is, of course, the case in all engineering application on Earth, because we know, if there is an S-curve going wrong or whatever, we know that. But in the case of SETI, we are just facing the peculiar case, the black sheep, because we do not know what the hell is coming inside. So rather than just ruling out all this, because it is computationally demanding, the suggestion is don't rule out anything and keep it, and we'll see what comes out of that. So I don't want to insist more. There would be more, but if you really want to know more about that, you read my book, and there is all the calculation that I have found in 20 years of time. So, conclusion of the story. This book is two-phased. First phase, space mission to 550U, that was conceived by Frank Drake for the good of SETI, but actually is now proving itself much more useful outside SETI. For instance, cosmology, as I said, in the microwave background. And also other things, you know, Alpha Centauri, the black hole at the galactic center, many other. And the second part of the book, on the contrary, is devoted to this algorithm, which is, again, was born out of SETI needs. But if you think carefully, of course, it applies to everything, because mathematics applies to everything. Thank you very much.
Fantastic. Thanks, Claudio.
Thank you.
If I may ask the first question, in your CMB mission, what sort of angular resolution would you get for looking at the CMB? How much of the CMB could you actually see?
You get 10 to the minus 8 arc second. I'll show you that. So I'm going back. Okay, here it is. So it's about 1 billion times better than the angular resolution of COBE, WMAP, and Planck.
So how much of the, I'm thinking of how much use would that be if you're resolving the CMB of just what's behind the sun? Are you actually going to see enough to make it useful for the cosmologists?
Well, the point is that we would be able to see the star formation, for instance, in much neater detail than we know about. But that also applies to cosmological objects. So, for instance, there has long been debates about what quasars really are. Are they, well, they are prototype galaxies, but okay, but then the stars must be there, and so on and so forth. My impression is that with such a huge improvement in the angular resolution, we would be able to find out whether there are stars within quasars or not.
Do you have any other questions?
Yes, as the focus extends to infinity, right? Are we at the focus of Alpha Centauri, or maybe at the focus of some galactic black hole already?
Yes. And
just sitting where we are, could observe the cosmic microwave background that way?
Yes, the answer is yes, and I thank you about that. This is a question that was asked to me many times. The answer is yes, but unfortunately there is one drawback. Just consider the nearest case, that is Alpha Centauri. Then you have to take into account the attenuation of the signal that takes place in between Alpha Centauri and where we are. And unfortunately, the attenuation, which goes with the 1 over the distance squared, is so large that we cannot use the Alpha Centauri lens, as you would be suggesting, or any other lens, even farther out, as an improvement to what we can do here. Okay? So the answer is, in principle, you are absolutely correct. But when you go down to the calculation, you find that the attenuation already for Alpha Centauri, and even worse for the nearby stars or whatever, is too big. And we cannot get it. Anyway, this is treated in my book.
Claudio, that actually may have answered my question, but I was wondering how sure we can be of the fluctuations in the microwave background, because they're supposed to be indicative of quantum fluctuations then via inflation causing variations in the microwave background. But how sure are we that they are not a series of distributed gravitational lenses where the sources are too far away for us to directly detect optically or by radio, but the fluctuations, they're producing those fluctuations?
Look, I don't know about that. This, let me tell you, this would require a study of the focal space mission just for cosmology alone. So no SETI, no anything else, but just for cosmology. We should do that, but you see, the difficulty for me is to convince the scientific community that focal is the first thing that we have to try, because it offers so much magnifications. So if I could answer very honestly to your question, my next step would be to go to Paul Davies, who appreciates all this, and say, look, you are a cosmologist. Now, would you please assemble a team of cosmologists? We would explain to them the focus space mission that they certainly don't even know about, because there are so many different topics of interest. And then we would go over to your question. At the moment, I have no answer for that.
So thank you for such an interesting talk. And as far as I can tell, you were just considering radio waves and microwaves. Could this be done in shorter waves,
yes.
optical?
Yes, it can. And actually, well, it can if we can overcome the corona problems.
Can you just block it with an occulter?
Yes, this can also be done, correct, yes. Look, this was actually the first thought ever about all this coming from Frank Drake. So when Frank Drake made the first presentation ever of the sun as a gravitational lens in Hungary in '87, which stunned me so much, he was just talking about that. I remember a sentence of his. He said, by virtue of this trick, you could see the people walking in the streets on some nearby planet. Now, this is easily said and difficultly computed, so I don't know the detail about that, okay? My honest opinion is that we would need to do one more study as the one for cosmology that I just mentioned, for this aspect, that is using the sun for optical.
Okay. And also following question, if you think about this in terms of telescope optics, if effectively you have a very chromatic lens with a very large central obstruction, have you considered how that affects the bandwidth in which you can image, and also the size of the point spread function, how that affects that?
Okay, thank you. Well, sorry to disappoint you. In my book, this is not considered, but I know that there were people, possibly Jeff Landis at NASA, NASA Glenn, who once mentioned to me the point spread function of the sun gravity lens. So you won't find this in my book, but if you talk to him, he may be able to say more.
All right, thank you.
In practical terms, it seems to me that that getting cosmologists on board to support the focal mission is difficult, given that you're talking about generations to get out to 763 AU, aren't you?
Yes. Yes, you're right. This, unfortunately, is one of the drawbacks of the mission, that is to get to 753 AU takes 50 years. It depends on the propulsion system. So the difficulty in, not so much in proposing, but in making this mission become a reality, is at least twofold. First, you need a strong scientific community supporting the idea, and this is why I thought of the cosmologists, because in my opinion they are the strongest group ever in the astronomical community. But apart from that, there is another awful issue, which is the propulsion system. There are different ways of conceiving propulsion for deep space mission like this one. I just mentioned one, the nuclear electric. What is this in plain terms? It means that you are using electric propulsion, but the energy comes from a nuclear reactor. Now, this brings more problems. First of all, electric propulsion works. For people who are not acquainted, essentially you have a gas, xenon usually, which is ionized, and then there is a set of electrodes that push that out, and they pick up the electrons when they get out, but they get out of the spacecraft with such a momentum that this pushes the spacecraft. It's not so much high, the momentum, but it is continuous. So it has been proven out of the question that within the solar system, this is excellent for planetary exploration. Okay? There are many missions, both American and European, that have been using that already, period. The question is, are we going to use nuclear energy to feed that? Oh my, this is not a problem, because the ecologists, of course, will say, no, 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 no. If an accident happens during the launch phase, you are responsible. It's true, but when you consider distances of that order, there is no other way, because there is no sun over there, no light. You realize the point. Even the Voyagers would have been dead long ago if they hadn't had a thermal generator. Please correct me if I'm wrong. Exactly. So here again is another problem. You know, we have to be careful, because if by any means the newspapers publish, oh, this guy wants to use nuclear electric propulsion to go to the sun focus, goodbye. We are everybody is against, you know, for emotional reasons. So the answer to your question is the times are huge, but it all depends on the propulsion system. Now let me just give you one more answer. Recently I was talking with people in the, not in the FTL business, but in other business called Vasimir, and very advanced propulsion system. Now they would love to try that, because so far all that has been on paper. Incidentally, the Russians, the Soviets, whatever you have to call them, already considered nuclear propulsion for their own mission. Then the Cold War ended, and the Russians handed over the things to the Western, but the Western didn't notice, or didn't notice appropriately. So recently there was a top Russian official saying, look, we have the nuclear propulsion, we want to use it. Now, if that will ever happen, I would respectfully ask the American community to do exactly the same as the Russians did, because they did the right thing in order to reach high distances. There is no way to escape. The distance is what it is, period. I don't know if I disappointed you too much. Is that the truth? Okay, of course. Well, people in the space business may have better answer than I can. Not today. Okay, good. Okay. Okay.
Okay. There's no further questions, Claudio. Well, we've got a small. Oh, we've got one quick one.
Nuclear radioactive powered battery you're talking
I would
about.
choose the second option. But you see, the full matter is completely in the set of question marks. Let me tell you more in detail. There was a set of conferences that you probably are acquainted with, the so-called STIFE, Space Technology and Application Conferences that were held in the late 90s, early 2000s at Albuquerque, New Mexico, just by chance, not too far from Los Alamos, okay? Just by chance. Now, there it is where we debated all these matters. So there are people who are definitely favorable to nuclear stuff. And who knows, perhaps the military are very favorable to nuclear stuff. But this is not known to scientists like myself. And so the matter is still undecided, okay? We have to decide what to do, period.
Claudio, as a small token of our appreciation, we have a little
Wow.
pin for you.
Thank you so much.
If you'll join me in thanking Claudio for his very fascinating.
Thank you. Thank you very much.